Hi, welcome back to General Chemistry 1. Now we're moving on to Chapter 5, and the first lecture is about individual gas laws. So what is a gas? We know gas is a property of a material. When we cool down the gas material, it will turn from gas to liquid. If we further cool down, we can turn the material from liquid to solid. So gas, liquid, solid are just three different properties or three different phases of one substance. And for gas, there are some properties that are unique. For example, it's compressible. If we have a certain amount of gas, we can shrink or expand its volume very easily. It's of course related to its pressure. Also, the gas has huge thermal expansion, which means the volume will react vigorously with temperature. If the temperature increases with a certain amount of gas, the volume will also increase. All the gas molecules are flow very freely in the gas environment, of course, and that leads to a low density of gas. And when we have different gas molecules mixed together, we will form a solution. Like we will have a gas solution made by different gas molecules. So when we have a liquid, we talked about in our last chapter, there could be some insoluble or soluble problems. But for gas, all types of gas will mix with each other very well. When we talk about pressure, pressure is defined as the force exerted per unit of surface area, or pressure equals to force divides area. And for gas, we need to use pressure, or pressure is one of the very important values or properties that describe a gas. For pressure, we have different units. And for 1 atm, that is actually one of the units used to describing the pressure at sea level, atmospheric pressure at sea level. It's atm. Also, there are a few other units. So I would like to mention two of them. One is Pascal. Okay, it's PA. This is an SI unit. It's not one of the 7 basic units, but it's still an SI unit. And if you are interested, the derived SI unit for pressure is per meter kilogram per cubic centimeter, per cubic seconds. So for the derived SI unit, it has to be made up by 7 basic SI units. So that's how it comes. We don't use the derived SI unit for pressure very often. Instead, we use par and also torr or millimeters of mercury as the unit more often. For the millimeters of mercury, it is converting the pressure or using the length, the height of the mercury column to indicate the pressure of the surrounding area, surrounding gas. It was derived, it was first brought up by the experiment. So before, when we don't know about pressure or we don't have a good way to measure the pressure of the gas, scientists did the experiment that in the tube, he filled in the mercury. So it was filled before. And then he turned the tube upside down. So some mercury will, leak out into the container. And the liquid of the mercury in the container will be higher than the opening of the tube. So no gas can leak from outside into the tube. Okay, so now we can see the mercury inside the tube will drop, but not drop all the way to the bottom. It will drop to a certain height and stop. So that's because we have pressure from the outside. And in this case is the atmospheric pressure. As we know, it's a physical property. In the continuous liquid or gas, the pressure at the same height or same elevation height are the same. So the pressure on the surface of this mercury liquid and the pressure of the mercury on the same height of that surface but it's underneath the mercury column, these 2 points are the same, have the same pressure. So the pressure outside on the surface of the mercury liquid, it experienced the pressure of the atmospheric pressure, so it's 1 atm. Well, here inside in the tube, it experiences the pressure put by the mercury column. So then this height of the column, because on top is vacuum, right? So this height of the column of the mercury can be used to describe how much the atmospheric pressure is. So that 760 millimeter of mercury, it's how it comes into being. We talk about many properties of gas. We mentioned, say, pressure, of course, the number of gas molecules, or the number of gas molecules, the temperature, and a few other properties. So scientists in history also studied those and find a few individual gas laws. Let's take a look at them one by one. So first is the Boyle's law. On the left is a device he used. He used U-shape device with one end sealed, the other open to air. So he seals some gas in the left end and seal the gas by a section of liquid mercury. If he pulls more liquid into the U-shaped tube, he can notice the pressure or the volume of the gas on the left decreases. Then he can put different amount of mercury, collect data, plot the data, and find the Boyle's law. So in Boyle's law, it means at constant temperature, the temperature does not change. The volume occupied by a fixed amount of gas is inversely proportional to the applied external pressure. So in other words, the volume of the gas, so this is the mass expression of the inversely proportion. Okay, volume and pressure are inversely proportional to each other. The temperature and number of gas is fixed. Okay, or we can write in another way. So that means at constant temperature and the number of gas, the more the pressure, the smaller the volume. The lower the pressure, the larger the volume. Okay, so this is Boyle's law. Also, we have Chelsea's law. So he used a device like this. There is a beaker and there is an open tube. In the tube, there is a mercury plug that can move up and down freely. So with that, we can treat, saying the pressure sealed by this mercury plug is always the same because that's determined by the atmospheric pressure outside, right? So what he does is he uses a thermometer to read the temperature inside of the surrounding water. The tube was immersed in the water. So when he heat the water up, heat will transfer to the gas. Okay, so the pressure of the temperature of the gas will also increase. Then he can take the volume of this pressure and then collect the data, do the plots, and find the Chelsea's law. Okay, so Chelsea's law is at a certain pressure, the pressures are the same. The volume occupied by a fixed amount of gas is directly proportional to its absolute temperature. And when we say absolute temperature, is the temperature in the unit of Kelvin. So in other words, in the mass expression, V is in proportional to T. Pressure and number of gas are fixed. We have other ways to write it, but if we understand that, so it's at fixed pressure and number of gas, higher the pressure, higher the temperature, more the volume. Lower the temperature, less the volume. Okay. Now, we can move on to the Avogadro's law. So Avogadro, you are familiar with him. He is the one first measure the, we named the Avogadro's number after him, right? So there was experiment that we also still have the free plug in a kind of tube. Then we trap some gas inside. If we create more gas inside, so originally we only have 0.1 mole of CO2, now we have 0.2 mole of CO2, double the amount of gas. We found the volume of this gas, the CO2 occupied also doubled. So for Avogadro's number, it's at constant pressure and temperature. The volume occupied by a gas is directly proportional to the amount of the gas. It's easy to understand, right? So the more of the gas we have, the more volume it occupies. We have this as a V proportional to N as a mass expression, or you can write in another way. So at fixed pressure and temperature, the more of the gas, the bigger the volume is. The less number of the gas, the less of the volume the gas occupies. Okay, so we introduced 3 different gas laws, and maybe I can help you to memorize them more easily. We have Avogadro's laws, V equals to constant times N. Boyle's law, V times P equals to a constant, and Chap's law, V equals to a constant times T. So in all of these 3 gas laws, we have 4 values: pressure, volume, number of gas, and temperature. Okay, those are not mentioned as variables in the gas laws are constant. And for all laws, the volume is one of the variables. And all of the gases are describing the relationship between 2 variables. One's volume and the other one, for Avogadro's law, you see, we can link Avogadro's law to the Avogadro's number that refers to the quantity of a gas, right? So Avogadro's law is a relationship between volume and number. We can say V1 over N1 equals to V2 over N2 because V over N is a constant. For Boyle's law, the other variable, besides volume, the other variable is pressure. You can remember BP, right? For Boyle's law is the pressure. So V1 P1 equals to V2 P2. And third, for Chap's law, besides one variable as volume, the other variable is temperature. Okay, Chap's law, temperature, CT. You can remember for Chap's law, besides volume, temperature is not a variable. So for that, V1 over to T1 equals to V2 over to T2. So all of the 3 gas laws, you can remember them individually, or in our next video, we're going to talk about ideal gas equation, and you can that will include all of these 3 gas laws. Okay, so beside these 3, there's another one called Amanton's law or Gay-Lussaca's law. So this one saying at constant volume, the pressure exerted by a fixed amount of gas is directly proportional to the absolute temperature. So this one is not, the 2 variables here is pressure and temperature. So it's different from before. And in this case, volume and number of gas are fixed. So we can say at fixed volume and number of gas, the higher the temperature, the higher the pressure. The lower temperature, the lower the pressure. All right, this is the end of this video. We described many gas laws. So in our next video, we're going to introduce the ideal gas law. See you there. Bye.